It might be one of the strangest archaeological missions ever undertaken in the Himalaya.
They are clearly protecting or preserving something that may or may not be under 3 miles of ice.
A remote cave under the Himalayas was kept off limits for generations, guarded as a sacred place.
Visiting the Crystal Ice Cave, it's a 100% natural ice cave, just exactly as nature gives it to us. Every year it's changing.
No digging, no research, no questions. When scientists finally stepped inside, they found a floor that had never been touched, a perfect time capsule beneath the dust. And under that surface were unmistakable traces of people who should never have been there at all, from a time older than every civilization we know.
You've never heard this?
No.
It's the greatest story ever, bro.
The Forbidden Cave on the edge of the Himalayas. On a winter night, a small research team stepped onto a frozen river in a high corner of China near the Himalayas. Their headlamps lit up the ice and the rocky slope ahead as they made their way across the river and up the pale cliff above it. Halfway up, a dark opening cuts into the rock. From the valley, it looks like a black mouth with a narrow path leading to it.
So we're inside the beautiful Crystal Ice Cave, and what's really special about this ice cave is it's 100% natural.
This is Baishia Karst Cave in Xiahe County in Gansu Province, on the northeastern edge of the Tibetan Plateau. The entrance sits a little over 10,000 feet above sea level, on a mountainside facing ranges tied into the wider Himalayan system. For people in the region, this cave has long been a holy place rather than a bare shelter. In Tibetan tradition, it is linked to Padmasambhava, often called Guru Rinpoche, and to the Bodhisattva Tara. Monks come here to fast, meditate, and recite prayers. Pilgrims climb to light butter lamps, press their foreheads to the rock, and sit in silence in the half-dark. A small temple building stands below the opening, and inside the cave, there are shrines, cloth offerings, and framed images set against the walls. Some say that secret tunnels run from this cliff deep under the mountains and open in another county more than 30 miles away, or that the cave is so long, no one has ever walked to its end. Because the cave is so important to the people who live there, Baishia stayed mostly untouched by science for a long time. Monks and local caretakers simply protected it and kept others away. Pilgrims and tourists were allowed to step into the front chamber to pray or take a look, but the ground under their feet was not to be disturbed. In the early 1980s, a monk who came here to meditate noticed something odd on that floor. Among loose stones, he found a heavy piece of bone, half of a lower jaw with large back teeth still sitting in it. He carried it to a senior religious teacher, who passed it on to experts at Lanzhou University. The bone was clearly human, but it did not look like the jaw of people living in the region today. For a long time, it sat in a university drawer, puzzling the few researchers who saw it and slowly gathering dust. That forgotten jaw hinted that Baishia might hold a much deeper past, buried under the shrines and prayer flags. By 2010, a team from Lanzhou University had begun to visit Baishia and other caves in the valley. They wanted to know how very early humans had learned to cope with the thin air and long winters of the high plateau. Still, every time they asked to dig inside the cave, the answer from the religious side was no. The cave was a living sanctuary. Turning its floor into an open trench felt wrong. For several years, the team worked around the edges instead. They walked the slopes, mapped the cliffs, and picked up stone flakes and broken animal bones lying loose near the entrance. In the middle of the decade, they carried out a careful survey inside the cave itself. On the surface of the floor, mixed with dust and bits of modern trash, they began to see more stone pieces that looked shaped by hand. That was the sign they had waited for. It suggested that long before the cave became a shrine, people had used it as a shelter or camp. Even then, they were not allowed to cut into the deeper layers. A slow, careful negotiation followed. The researchers explained that they did not want to damage the religious life of the cave. They wanted to learn who had lived here long before the first monastery in the valley, and how they had survived in such thin air. They promised that any work would be limited, quiet, and respectful. Religious and cultural officials weighed these requests against their duty to protect the shrine. Meeting followed meeting. Seasons passed. At last, a narrow path forward was agreed upon. The team would be allowed to open only a small excavation at the entrance of the cave and only under strict rules. They could not dig near the shrines or altars. They would stay away during busy times, such as major festivals. Most striking of all, they would carry out their work at night in the dead of winter, when no visitors were on the path and the monks were resting in the monastery. That is why, on those winter nights, the group once again found themselves on the frozen river in the dark. The ice under their boots groaned. Above them, the cliff wall rose steep and pale, catching the weak beams of their headlamps. They climbed through low shrubs and loose stones, sometimes sinking into pockets of snow. Each person carried a pack filled with trowels, sample bags, and small lamps. Their breath turned into white clouds in the air. At the cave mouth, the wind eased. They ducked inside, where the ceiling hung low, and the air smelled of dust, old smoke, and butter lamps. Deeper inside, they had marked out a neat rectangle on the floor with string and tape. This was their only approved dig area, set a little away from the shrines, but still within the entrance chamber. At first glance, the ground looked flat and plain, a mix of packed earth and small stones covered in footprints. But the team knew that under that thin, worn surface were older layers stacked over centuries, built up as soil washed in, ash settled, and pieces of rock fell from the ceiling. They spread plastic sheets and laid out their tools. Then one of them knelt at the edge of the square and began the first careful cuts. Instead of swinging a shovel, he used a small trowel to peel away thin slices of the surface. Each slice went into a labeled bag. Under the top crust, the soil shifted in color and feel. Some bands were darker and more crumbly, others lighter and more sandy. To trained eyes, this was the first clear sign that the floor held a long and layered record of use. Soon, the quiet work began to pay off. In one shallow layer, a small stone flake with a razor edge appeared in the sieve. In another, deeper layer, the team found a larger stone piece that had clearly been struck and shaped by human hands. More followed from different depths. Flakes, cores, and simple tools made from local rock. These were not stones dropped from the roof of the cave. They were the leftovers of people sitting on the floor and shaping tools long ago. Mixed in with the stones were animal bones. Some were thin, the size of finger bones. Others were thicker, like parts of the legs of medium or large animals. Several had been cracked open, and the break surfaces were sharp and clean, as if someone had struck them hard while the bone was still fresh. In a few places, dark streaks in the sediment turned out to be thin bands of charcoal, the tiny remains of old fires. Layer by layer, the picture inside that small square changed. What had looked like a simple, dusty floor used for prayer revealed traces of repeated visits reaching far back in time. Fires had been lit. Animals had been brought in and cut up. Stone had been worked into tools. After each visit, bits of ash, bone, and broken rock sank into the ground. Later, fresh soil and dust settled on top, sealing those traces in place. No one dug here deeply in later centuries, so the stack of layers stayed in order, like pages in a closed book. The team still could not say who had left these marks, or exactly how old the deepest layers were. What they did know, standing in the cold cave with trowels in their hands, was that the floor beneath the shrine was not simple at all. It held a thick, untouched archive of human activity at a very high altitude, formed over a span of time that clearly reached far beyond written history. To find out who had lived there and how long ago they had used this high mountain shelter, the team now had to take what they dug up back to the lab. Tracing the cave's oldest visitors through bone and dust. Those bags of soil and broken bone that left the cave in the dark didn't look like much. In the labs at Lanzhou University, they ended up on a table beside the heavy half-jaw with two large molars that had been sitting in a drawer for decades.
This discovery allows us not just to say we have Denisovans there in Tibet, but also to identify some other fossils that has been found in the past in China.
That jaw did not look like a normal modern human jaw, and it did not match classic Neanderthal fossils either, so nobody knew quite what to call it. In the late 2000s, Chinese researcher Chen Fahu and his colleague Zhang Dongju decided to reopen the case. They noticed a thin, chalky crust on the outside of the fossil. That crust had formed from minerals that slowly build up when water rich in uranium drips over bone and turns into rock.
The orange-brown hue suggests the presence of iron or other minerals mixed within the limestone.
If they measured how much of that uranium had turned into thorium, they could work out how long the crust had been growing. Using this method, they found that the crust itself was at least about 160,000 years old, which means the jaw trapped under it had to be even older than that. The team still needed to know what kind of ancient human it belonged to. There was no usable DNA left inside the fossil, so they turned to the proteins locked in the hard tissue of the teeth. They scraped tiny samples of tooth material, broke the proteins into fragments, and ran them through a mass spectrometer, a machine that weighs molecules very precisely. The pattern of protein fragments acted like a barcode. When they compared it with patterns from known fossils, it matched a mysterious group first found in a cave in Siberia, the Denisovans, an extinct branch of humans that were close cousins of both Neanderthals and our own species.
And this way to relate them to this group of the Denisovans. And by putting together all these fossils,
That result made the Xiahi jaw the first confirmed Denisovan fossil ever found outside Siberia and the oldest known human fossil on the Tibetan plateau. It showed that this high, cold region had already been home to these ancient people at least 160,000 years ago, but one jaw without a clear spot in the cave could not tell the whole story. To understand how long these people had used Baishia and how often they came back, the team needed dates from the cave floor itself, layer by layer. So they turned to the bags of soil and broken bones they had dug up during those winter night excavations. For the younger parts of the sequence, which covered the last tens of thousands of years, they used radiocarbon dating. This test measures how much of a weak, natural form of carbon remains inside bone or charcoal. Living things take in this special carbon while they are alive. After they die, it slowly breaks down at a steady pace. By checking how much is left, scientists can estimate how long ago the animal died or the fire burned. For deeper, older layers where radiocarbon no longer works, they used a method called luminescence dating. Tiny grains in the cave sediment act like miniature time capsules. While they sit buried in darkness, natural radiation from the ground makes energy build up inside them. When the grains are exposed to light in the lab, they release that stored energy as a faint glow. Measuring that glow tells researchers how long it has been since those grains last saw daylight, which usually means the last time the surface of that layer was open to the air. When they combined all the tests, a clear timeline appeared. The deepest layers with stone tools at Baishia were about 190,000 years old or older. Above those were more layers with tools and animal bones. The youngest, well-dated layers with clear signs of human activity were roughly 40,000 to 30,000 years old. This meant the cave had not been a one-time shelter. It had been visited and used again and again over at least 150,000 years. That still left a key question. The jaw and the cave layers were old, but who exactly had been using the cave during all those different periods? To answer that, the team tried something new. Instead of waiting for full human skeletons, they looked for traces of DNA hiding in the cave dirt itself. Every time a person or animal bleeds, sweats, or goes to the bathroom, tiny bits of genetic material fall into the soil. In a cold, dry cave, some of that DNA can survive for a very long time. From each major layer in the Baishia sequence, they took small bags of sediment and treated them almost like blood samples.
They're unearthing bones and remains, as well as tools and artifacts.
In clean labs, they washed out fragments of ancient mitochondrial DNA, the type that sits in the energy factories of cells, and is often better preserved than the DNA in the cell nucleus. They then compared these short pieces with reference sequences from known human groups. The key result was simple, but powerful. Layers that dated to roughly 100,000 and around 60,000 years ago, and possibly as recent as about 45,000 years ago, contained mitochondrial DNA from Denisovans, not from modern humans. The fact that their DNA appeared in several separate layers showed that these people kept returning to this cave over tens of thousands of years, not just during a single short visit. The team then turned to the bones scattered through the cave floor. Most of them were tiny, splintered fragments, broken up by time and by ancient butchering. Many carried cut marks or signs of burning, but to learn which bones were human and which belonged to animals, they needed a way to check thousands of small pieces without destroying them. This is where a method called zooarchaeology by mass spectrometry, or ZooMS for short, came in. ZooMS works with collagen, the main protein in bone. Different species have slightly different versions of this protein. In the lab, scientists take a tiny scraping of bone, break the collagen into pieces, and run those pieces through a mass spectrometer. The pattern of fragment weights forms a kind of barcode. By comparing that barcode to a library of known patterns, they can usually tell whether a fragment came from a goat, a deer, a hyena, or a human, even if the bone is too small to identify by eye. When this collagen fingerprinting was applied to thousands of bone pieces from Baishia, one fragment stood out. It was part of a rib from a layer that fell between about 48,000 and 32,000 years old. The collagen pattern in that rib did not match goat, yak, or any other animal. It matched Denisovans. In other words, the same kind of ancient human seen in the jaw and the sediment DNA was now directly identified in a new bone from a much younger layer in the cave. This single rib, sometimes called Xiahi 2, pushed the known presence of Denisovans on the plateau forward in time. It showed that they were still living in or visiting Baishia as late as the tail end of the Ice Age, when modern humans were already spreading widely in other parts of Asia. That makes the Baishia rib the youngest Denisovan fossil that has a secure scientific age, younger than the famous bones from Siberia. The lab work on the jaw, the cave sediments, the DNA, and the rib answered two big questions. Who was in this sealed Himalayan cave, and how far back in time their visits reach? What these tests do not show is how life in that thin air actually felt from day to day. The next step is to follow these Denisovans out of the lab reports and back into their world, an ask how they found food, handled the cold, and managed to live for so long on the roof of Asia. Life above the clouds in the Ice Age. If you are not used to it, staying a night on the high Tibetan Plateau feels like trying to breathe through a thin straw. At heights between about 10,000 and 14,000 feet, the air holds far less oxygen than at sea level. Most visitors feel pounding headaches, a racing heartbeat, and a heavy, slow tiredness. In bad cases, their lungs fill with fluid or their brain swells, a condition people simply call high-altitude sickness. The body tries to fight back in a blunt way. It pumps out extra red blood cells to grab more oxygen from each breath. At first that helps, but over time, the blood can become too thick. The heart has to work harder to push it through narrow vessels, and the risk of clots and stroke goes up. This is why doctors warn people who live at low altitudes not to move straight into places as high as the Central Plateau. Yet millions of people in Tibet live at these heights every day without bottled oxygen. One big reason lies inside their blood. Studies of Tibetan families show they share special versions of several genes that control how the body reacts to low oxygen. One of the most important is a gene that scientists call EPAS1. This gene works like a switch that tells the body when to raise or lower red blood cell production. In most people, low oxygen flips that switch all the way on. In Tibetans, their version of EPAS1 keeps it partly turned down, so their blood does not get dangerously thick. Genetic work over the last decade has traced this helpful version of EPAS1 back to Denisovans. When groups of early modern humans moved into Asia and met Denisovans, the two groups had children together. Some of those children carried Denisovan versions of genes that handled low oxygen better. Over many generations on the plateau, those helpful versions spread through Tibetan communities. The animal bones from Baishia fill in what life up there looked like. When researchers sorted and identified thousands of broken bones from the cave, they found that most came from blue sheep, also called barl, a wild mountain goat that still lives along the high ridges. Other bones came from wild yaks, deer, and wild cattle, as well as from meat-eating animals like hyenas, wolves, Tibetan foxes, snow leopards, and birds such as golden eagles and pheasants. These bones were not lying there by chance. Many of the limb bones had been hit hard and split lengthwise in ways that match known patterns of people cracking them open for the rich marrow inside. Some carried straight-cut marks from sharp stone edges, often near joints where meat is sliced away. Others were darkened and cracked from heat, showing they had been near or inside fire. Taken together, this pattern shows that Denisovans were hauling animal parts into the cave, skinning and cutting them, roasting meat and smashing bones to get every last bit of food out of them during harsh Ice Age seasons. The mix of animal types tells its own story. Blue sheep prefer steep rocky slopes. Wild yaks range over open grassland. Deer and wild cattle like areas with more plant cover. Predators such as hyenas and wolves follow the herds and also scavenge. For Denisovans to leave remains from all of these animals in one cave, they had to use flexible tactics. At times, they were hunters, tracking herds along ridges and valley floors. At other times, they were likely scavengers, cutting into carcasses that meat-eaters had already killed. In a world where winters were long and the air was always cold and thin, any usable meat or marrow was too valuable to waste. Life on the plateau was not only about hard work and hunger, though. A place called Kasong, in the central part of the Tibetan Plateau, gives a rare glimpse of children at play high in the Ice Age mountains. There, near old hot springs, more than 13,000 feet above sea level, researchers found a block of pale rock covered with handprints and footprints. The rock is travertine, a kind of limestone that forms when mineral-rich hot spring water cools and leaves its load of lime behind, a bit like the scale that builds up in a kettle, except on a much larger scale. Tests on the travertine show that these prints were pressed into soft, warm deposits sometime between about 169,000 and a little over 220,000 years ago, deep in the middle of the Ice Age. The sizes of the prints match two children, one roughly the size of a 7-year-old, and the other close to a 12-year-old. The handprints and footprints form clear, repeated impressions that do not look like random walking. Instead, the kids seem to have placed their hands and feet on purpose, pressing them into the mud as it cooled, then pulling them away and doing it again. Those children almost surely belonged to a high-altitude human group closely related to the Denisovans at Baishia. Their play has outlived them by hundreds of thousands of years. Today, their prints are often called the earliest known example of fixed artwork in the world. The plateau around these sites was never empty. While Denisovans were using caves and hot springs, early modern humans were pushing up from lower ground. At a place called Nuyadevu, nearly 15,000 feet above sea level, stone tools show that modern humans reached the interior of the plateau roughly between 40,000 and 30,000 years ago. This is, so far, the highest very old camp of its kind that archaeologists have found anywhere on Earth. Other work has shown people living for at least 5,000 years along the lower flanks of the plateau, in what some researchers call the shadow of the Himalayas, long before recorded history. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.